So you missed out on the Fe3 plus 2 plus equation. Like you're supposed to include all those equations that involved, this was 0.77 volts. So your reaction had Fe2 plus, right? So you should have added this equation as well. And so I'm just going to quickly do this. Can you just K plus 1 electrons in equilibrium with K? That is minus 2.92 volts, right?
Yes.
And then you have, what is the Fe2 plus equation that you used? It's gaining 2 electrons.
Yes. Fe2 plus 2 electrons is Fe. It's negative 0.44.
4 volts, and then you have the because if you look at your I think you can't use Cl2. Like, let me just quickly recheck your result, because you selected which equation did you select? You selected the Fe equation. You don't have Fe, right? You've got Fe2 plus. You don't have Fe.
Selected 2Cl negative and MnO4. Cl2 and MnO4. I selected both of those equations.
But at the bottom, it has Fe in it. Because it's just.
Oh, it's my mistake.
Anyways, just a second. You selected that, right? And that, yep, Cl minus 1 is the lower potential. You do have Cl minus 1, that's fine. And the other one is, so it's going to work with Cl minus 1, but you missed out on this equation, which is why the end result would be different. So if you had used Cl minus 1, your working would have been fine. There's nothing wrong with the working, except you missed on one of the equations. So I mean, you've got MnO4 minus 1. Just let me quickly, plus I think 8H plus 1 plus 5 electrons. Remember, MnO4 minus 1 also has 2 equations. And this is going to be 4H2, I think. And this is, what's the voltage on this? It's
1.52.
How much? 1.?
1.52.
1.52. Can you just quickly have a look on the data booklet and see if there's another equation for MnO4? I think there is, with 3H plus 1. All right. Like that. Let me just open the data booklet quickly. So here's the data booklet is actually here. So MnO4 minus 1 plus 4H plus 1, you've got another equation. So let me copy that one. It's 4H plus 1 plus 3 electrons, right? And it's an equilibrium with, and it's 1 point, it's going to form MnO2. And what else? It's going to form 2H2O. And this is actually what, 1.67 volts, right? So that's 1.67 volts. So you missed out on that equation as well. That's another one that was missing from your working. And what's left? I don't think anything is left. The Cl2 equation, I'll just add that in. Cl2 plus 2 electrons in equilibrium with 2Cl minus 1, right? So that's one equation. So who gains electrons? The one that has the highest potential, which is going to be the 1.67 volts. That's the one that's going to gain electrons. And there's nothing wrong with that because you've got MnO4 minus 1, you've got H plus 1 as well. So fine, they're going to gain electrons. So that's fine. There's nothing wrong with this equation. Is that clear? Raji, is this clear? And what about who's going to lose electrons? The lowest is minus 2.92, but it can't lose electrons. Why? Because you don't have potassium. So that's out of the question. Who's the lowest potential now? It's this one. But again, you can't use this because you don't have iron. Then who's the lowest potential out of all of them? It's
plus.
which one? Yeah,
FeC plus.
yes. I mean, this is 1.36 volts, the CL1. So the lowest one is the Fe2 plus equation. That's the one that's going to lose electrons. And you do have Fe2 plus, so that's fine. There's nothing wrong with that. So it's basically this equation. That's the one that has the greatest tendency to lose electrons. That's the one that has the greatest tendency to actually gain electrons. So it's going to be a reaction between these two. Is this clear?
Yes, it is.
So just remember that when you're looking for equations, like the reactants can have multiple equations. I mean, just don't settle for one. Like if you just found one Fe2 plus equation, there could be another Fe2 plus equation. Like you got an equation for Fe2 plus that's gaining electrons. You got an equation for Fe2 plus that's losing electrons. It's in equilibrium with Fe3 plus. That's in equilibrium with Fe. So MnO4 minus one. There are multiple reactions that could happen to it. Each one having a different potential. So that's your final overall reaction. Now, I mean, is the concept all clear, right? Is it clear?
Yeah.
So now slightly more difficult, same thing, but slightly more difficult things uh, related to this. And that is that sometimes you're going to have some chain reactions. I mean, it's not a chain reaction. I just call them chain reactions. What that means is that you're going to have one redox reaction followed by another redox reaction, and maybe followed by a third redox reaction. So you can have multiple redox reactions. One example is tin reacting with iodine. One of them is tin reacting with iodine. And now what happens in this reaction is, and I think iodine is in excess. So first thing, what's going to happen in this reaction? I have two reactions. I've got tin and I've got iodine. Iodine is, I think it's iodine plus 2 electrons in equilibrium with 2i minus 1. So there's only one equation related to that, and that I think is 0.54 volts. Okay, so that's one equation. See, where's the data booklet? Just a second. So that's the iodine equation, and you've got 0.54. That's fine. And the other one I'm looking for is the tin equation. Tin has, and it should involve tin. Tin only has one equation. That's this one. So it's what, 10 2 plus in equilibrium with gaining 2 electrons to form tin, or vice versa. And the value is minus 0.14 volts, right?
Yes.
So that one has a value of minus 0.14 volts. So let's.
How about SN4 plus?
Which one? SN4
The
plus?
one below.
Remember, my reactant is 10. So I'm just looking for equations where I have 10. That's it. Like the one below has 10, it's talking about 10 2 plus changing into 10 4 plus or vice versa, right? So I don't have either one of them. I have 10. So I'm just going to look for the reaction that involves 10. And there's only one of them, right?
Yeah.
So it's simple. Who gains electrons? I mean, you just have two equations. So the higher potential gains electrons, the lower potential loses electrons. And do I have the reactants? I do have I2 that's gaining electrons, and I do have tin as well. That's the one that's losing electrons. So, and the electrons gained and lost are also they're also equal. So I can make up the overall reaction, which is going to be in the first one. The reactant is going to be I2. And in the second one, the reactant is going to be 10 SN. And the product is going to be, in the first one, the product is going to be what, 2i minus 1. And in the second one, the product is going to be 10 2 plus, right? And I can calculate the E naught cell for this. It's a positive feasible reaction. which is higher potential, reduction potential minus oxidation potential. So 0.54 minus minus 0.14. And that is going to give me what, 0.68 volts, right? Is this clear? We've got a reaction. Okay, is it?
Yes.
So the next thing is, so the next thing is, what is a chain reaction? A chain reaction is, what do I have in my beaker after the first reaction? So my beaker has my products. What are my products? My products are, I've got 2i minus 1 and I've got 10 2 plus. So my beaker contains I minus 1 and it also has 10 2 plus, right? Those are my products that are formed. But if you look at the original reaction, it said that iodine is in excess. That means there must be some leftover iodine as well, right? So
Yes.
what I so basically what I'm going to try and figure out now is, I'm going to take the beaker and I'm going to try and see if there's going to be another reaction. Is there going to be another reaction in the beaker? Like that's, so let's ignore the previous reaction. We know this is the end result of the previous reaction. So the previous reaction is over. That's done with. So we're going to try and figure out, will they react again? And will there be something else that's going to be produced now? So what do I have? I've got I minus 1. So I'm going to take the same equation, which is I2, because for iodine, I just have one equation. 2i minus 1, and it's 0.54 volts. Now, the thing is, I've got 10 2 plus, right? So I'm going to write down the equations for 10 2 plus now. Something might happen to 10 2 plus. So 10 2 plus is involved in two reactions. There's 10 2 plus gaining 2 electrons to form 10, which is, we're talking about this one. That's minus 0.14 volts. And then you've got this other one as well. That's 10 2 plus can turn into 10 4 plus as well. So 10 4 plus in equilibrium with gaining 2 electrons, equilibrium with 10 2 plus. And that one is 0.15 volts, right? So that one is 0.15 volts. And iodine is the same one, right? So I've got these three things. So who's going to gain electrons? It's going to be the first one. And fine, I do have iodine, right? So that's fine. That's the one that's going to gain electrons. Ranjini, is this clear?
Yes. Yes.
And who's the lowest potential? It's this one, right? That's the one that's going to lose electrons. But I don't have 10. I don't have 10 anymore. I mean, there is no 10. I mean, there's 10 2 plus, but there is no 10. So I'm not going to use that. Which one is the lowest potential now? It's this one.
0.15. Yes.
So I'm going to use that. And I'm going to just ignore this equation, cut it out, and find out the overall reaction, which is going to be I2 plus 10 2 plus. Those are my reactants, and the products in both reactions are, in the first one it's 2i minus 1, and in the second one it's 10 4 plus, right? So I've got another reaction going on now after the first has happened. So there's a second reaction, and we can combine the two reactions together. Like so there was this first reaction. Now look at this carefully. There was initially what happened was 10 got converted into 10 2 plus. Then what happened was 10 2 plus then further got oxidized to 10 4 plus. And I can combine the two reactions together. So basically the reaction now has two steps. So what I can do is I can add up both reactants and both products. If I do that, add up the reactants, it's going to be I2 and I2, that's 2I2. So yeah, I'm just adding up the reactants of both reactions to 2I2 plus it's 10 plus in the bottom reaction, the reactant is 10,2 plus. And my products are, in the first one, it's 2I minus 1 and it's 10,2 plus. And in the second one, the product is again 2I minus 1 and it's 10,4 plus. And if I look at this overall reaction, I'll figure out that the 10,2 plus gets cancelled out. So basically, at the end of the day, it's 10 plus 2I2, and they're reacting together to form 4I minus 1 plus 10,4 plus. So that is my overall reaction. The reaction happened in 2 steps. You had step 1 and you had step 2. So tin got oxidized to tin 4 plus eventually, but it happened in 2 steps. It got oxidized to tin 2 plus first, and then it further got oxidized to tin 4 plus. Is this clear?
Yes.
Now, not all reactions will have multiple steps. The ones that are going to have multiple steps are the ones where you have multiple equations. Like you have to watch out for this. Like tin 2 plus can actually end up, tin can actually get oxidized up till tin 4 plus, right? So you have to watch out for this, that tin is going to have multiple steps. Similarly, a lot of substances over here, look at vanadium. Vanadium can have multiple steps. Like vanadium can go from vanadium to 2 plus, then vanadium 2 plus can turn into vanadium 3 plus. Then that vanadium 3 plus can turn into, I don't know what this is. This is plus 4. This is V plus 4, right? And this V plus 4 can get further oxidized to, I think, V plus 5. So it can continue to get oxidized, right? So you have to, now you don't have to worry about sodium because sodium only has one oxidation, one equation, right? So there's not going to be any multiple steps. Sodium will just turn into sodium plus 1. That's about it. But for others that have,
How about oxygen?
the same can happen to, these are all, oxygen turning into -2, that's -2. Over here, oxygen is turning into, this is still -2. So it's the same. It's not getting further reduced. Oxygen turning into, this is -1. So that can happen to oxygen as well. Like it can first turn into, it can go from 0 to -1. And then that -1 can get further oxidized to -2. It can happen to it. But the more important one, we're going to go back to the Mn equation. Like look over here, Mn has a lot of equations. It's Mn turning to Mn2 plus, Mn2 plus turning into Mn3 plus, Mn4 plus in equilibrium with Mn2 plus. This is, I think, +6, and this is +7. So it has a lot of equations. So I'm going to revisit the last equation that we did, the last one, the iron one, right? We said that this is, we didn't write the overall equation, did we? We didn't. Let me just quickly write the overall equation first. So we're done with the first step, right? That's the first step. We're going to try and figure out, is there going to be another step? So Fe needs to be, I think, multiplied by what? It should be multiplied by 3, right? To balance the number of electrons. So I'm going to make the overall equation. So that's going to be, the reactant is going to be 3 Fe2 plus. And in the bottom one, it's MnO4 minus 1 plus 4H plus 1. And the products I'm going to have. So the products are going to be, first one is 3Fe3 plus. And in the bottom one, it's MnO2 plus 2H2O. So those are the, so that's the first equation, right? So you combine. So let's think of a beaker. What does a beaker contain now? That's step one. So it's got MnO2 now. And in this case, let's assume that this is an excess. As remember, you can assume that anyone could be in excess because as the reaction is proceeding, the reactants are still there. So Fe might still be there. MnO4, but at the moment, let's assume that Fe is in excess. I mean, just to simplify things, let's assume that Fe is in excess. So my products are going to be MnO2, and it's got Fe3 plus. It's got water. We don't care about water. Water is by default everywhere, so water is always going to be present. And let's assume that some of the Fe2 plus is still there. You still have Fe2 plus in excess. Will there be a further reaction or not? So if I write the Fe3 plus one electron in equilibrium with Fe2 plus, I'm just going to shorten this because I'm not going to write all the other equations because they're not going to work. So we're just ignoring that, ignoring them. Like the iron equation is not going to work because it's minus 0.44 volts. That's the lowest potential. So it's going to lose electrons anyways. And we don't have iron, right? So I'm not going to write that. Is that clear?
Yes.
So I'm going to find equations for MnO2 now because my MnO4 has now turned into MnO2. So if you look over here, there's an equation for MnO2 acidified. So let's talk about that equation. I'm going to copy that one. Because I do have MnO2, the solution is still acidified. It's got acid in it, 4H plus 1, and plus 2 electrons. And it's in equilibrium with Mn2 plus 2H2O. And the E naught is what? 1.23 volts. So coming back to this. So remember, I mean, you can do the whole thing. You can write all equations involving Fe3 plus Fe2 plus. I'm just ignoring all of them because they're not going to work. This one is 0.77 volts. Okay, we've actually written those down there in front of you. The iron equations are not going to work. I mean, especially this one. It's not going to work. The others are not applicable anymore because we don't have MnO4 anymore. So who's going to gain electrons out of the two? It's going to be MnO2, right? And
Yes.
who's going to lose electrons? It's going to be Fe2 plus, right? So we have another reaction happening. I'm going to multiply this by 2. And I'm going to write the overall reaction, which is going to be 2Fe3 plus MnO2 plus 4H plus 1. And the products I'm going to have in the first one, it's 2Fe3 plus. Actually, I got this wrong. I think this should have been, the reactant was 2Fe, 2 plus, right? Just hold on. Just a second. So this would have been Fe 2 plus, and the product over here would be Fe 3 plus, and it's going to be Mn 2 plus 2H2O, right?
Yes.
So that's my second reaction. And that's it, chale. Can you hear me?
Yes.
So is this clear that you have another reaction, which is so basically you now have two reactions. The one in blue. So MnO4 first got reduced to MnO2, and then that MnO2 got further reduced to Mn2 plus. Is that clear?
Yes, sir.
And you can combine the two reactions together. Uh, so one way to look at these reactions, because it becomes difficult, and one way to look at these reactions is, think of this over here. You had Fe2 plus, right? And it was getting oxidized. That means it lost electrons. Like I can do the working here. So I had Fe2 plus, and it was losing electrons. Who loses electrons? The one that has the lower
Lower
E.
potential.
So MnO4 was the one that was gaining electrons. I mean, that was the one that had the highest E naught, right? Is that clear?
Yes.
And then that MnO2, it turned into MnO2. And then that MnO2 also gained electrons because it's still the higher potential compared to the Fe equation, right?
Yes.
I mean, after the first step, like ignore this equation, the first thing happened. And Fe was still the lower potential. So Fe was still losing electrons and the MnO2 was still gaining electrons. It got further reduced, right? Now, the question is, will Mn2 plus get further reduced? Like you have Mn2 plus now, will it get further reduced by Fe? It won't, because this is a very low potential. It doesn't like to gain electrons. I mean, compared to the Fe equation. Is that clear?
So can you please repeat it?
See, this is what's happening, right? Fe was the lowest potential. So the lowest one likes to lose electrons. So it's going to lose electrons, right? Fe is going to lose electrons.
Yes.
MnO4 was the higher potential, so it gained electrons, turned into MnO2. MnO2 was still the higher potential, like it was 1.23, that was 0.77. So it also started gaining electrons from Fe, right? Is that clear?
Yes.
And what about the third reaction? After MnO2, it turned into Mn2 plus, right? So now you have what? You have Mn2 plus. So if Fe were to lose electrons, will Mn2 plus further get reduced? It's not going to get further reduced because it's a very low potential. Who gains electrons? The one that has a higher potential. So Mn2 plus.
There's no Mn in the solution.
Hmm?
So it can. And Mn is not present in the solution, so it cannot.
Mn, yeah. I mean, because MnO4 was turning into MnO2, then MnO2 was turning into Mn2 plus. They were all getting reduced because Fe was constantly losing electrons, right? Because it had the lowest E naught. So the other ones were gaining electrons. It turned into MnO2. Then MnO2 got further reduced to Mn2 plus because it was still the higher potential, right? And then it stopped. Like it's going to stop gaining electrons after that. Because once it turns into Mn2 plus, it can't gain electrons because it's a very low potential compared to this one. And the reverse is not possible because you don't have Mn. Is that clear? So So that's how you're going to do that. Now, one trick about this equation, and especially for this equation, and that is instead of going through all this, because it's going to waste a lot of your time, make sure you remember this. Instead of going through all this and then writing the simplified equation, when you, because the Fe and KMnO4 titration is a very popular titration. One thing that you should remember is that when you have this Fe reaction and you have a KMnO4 reaction, go with the 1.52 volt equation. I mean, you just use these two equations and you'll end up with the final answer without going through all the steps. Even though 1.52 is not the highest potential, right? The 1.67 volt equation is the higher potential, right?
Yes.
But the shortcut is, I mean, you can even try this. Like, what's the overall equation? You add this equation with this equation, right? You add up the reactants, you add up the products, then you simplify things. And at the end of the day, what will happen is the MnO4 minus 1 is turning into what? It's turning into Mn2 plus, right?
Mn2 plus.
So instead of going through all of that, especially for Mn, because this is a very popular equation, the easier method is just don't go with the 1 point. I mean, just don't go with the steps. Right in the beginning, take this as the higher potential and select the 1.52 volt equation instead of the 1.67 volt equation. So you'll automatically end up with the final answer.
Okay.
Is that clear?
Yes.
So just remember this hack because you don't have that much time in your paper to actually go through all of this. So that's about this. There's one more equation which is also very which was given in your exams. So this one becomes easy. Just remember the Fe2 plus MnO4 minus 1 equation becomes easy if you hadn't selected this one. If you had gone with this one, you would have reached your final answer straight away. So remember this hack for this equation. You've gotten questions about 10. There's actually one very difficult question that students got, and that was vanadium with excess Fe3 plus. Just a second, let me. Vanadium. Yep, I think it's Fe3 plus. So vanadium with excess Fe3 plus. That was a question, and that had a lot of chain reactions because remember, vanadium has many equations. It's got a lot of equations. So, I mean, I can try and do the working. I mean, straight away over here. So I'll just add in the Fe3 plus equation. Now this is 0.77 volts, right? So, and remember it's Fe3 plus with vanadium, right? So which one is the vanadium equation? It's this one, and this is the Fe3 plus equation. So who's going to gain electrons? Vanadium only has one equation, which is this one. That's the only place where vanadium is. So this one is the higher potential. That is the.
Yes, this will gain electrons and that will lose electrons.
That will lose electrons, right? Then it forms V2 plus. So that's step number 1. Now, will V2 plus further gain electrons? I mean, still the lower potential is minus 0.26, right? And this is 0.77. So once V2 plus is formed, V2 plus is going to get oxidized further. Is that clear?
Yes.
Because iron is still the higher potential, so it would still like to gain electrons. So if vanadium 2 plus is formed, it will lose electrons further. Then you have V3 plus now. Now tell me V3 plus, will it lose electrons further or not compared to iron? It will, right? It's still the lower potential, right?
Yes.
And then it forms VO2 plus. Will VO2 plus then lose electrons further?
No, it won't.
It won't. So the reaction would kind of stop over here. So you got this equation. So basically it's 3-4 different reactions that are happening. The first one is iron 3 plus gains electrons and vanadium loses electrons, forms V2 plus. Then the next reaction is once V2 plus is formed, iron is still gaining electrons, and the V2 plus will still further get oxidized because it's still the lower potential. And then you have a third reaction with iron again. Iron is still wanting to gain electrons, and V3 plus will still lose electrons to form this. So that's three separate equations, three separate reactions. And you can try. So you got a question for this for 3 marks. We can try and write the equation. What is the first reaction? The electrons need to be balanced. So I think this needs to be doubled. So I'm just going to quickly write the first reaction with vanadium, right? So vanadium is the reactant. And over here it's Fe. And the other one is vanadium 2 plus. And over here it's 2Fe2 plus. So I think that's the first reaction, right? Is that clear? And then you have the second reaction, which is again with the V2 plus. So now you have V2 plus, and now the electrons are equal. So I just need Fe3 plus. And it turns into V3 plus Fe2 plus again. So that's my second reaction. And the third one is then my V3 plus H2O again reacts with Fe3 plus and ends up forming, what does it form? It forms a VO2 plus. So it's VO. So it's VO with a charge of 2 plus 2H plus 1, and Fe again turns into Fe2 plus. That's my third reaction. That's when the reaction stops. And we can make a combined reaction. Make sure you just add up the reactants and the products. The things that are appearing on both sides are going to get cancelled out. So V3 plus will get cancelled out. Fe, so it's V plus 4 Fe 3 plus there is water as well that's involved. And the product over here is VO2 plus 2H plus 1 plus 4 Fe. So that's my final, if I add up the reactants and the products and I cancel the common terms on both sides, just like a math equation, I get this final equation. So Raji, is this clear?
Yes, sir.
So remember, most reactions are not going to be chain reactions. You've gotten this, and most questions that you're going to get are not going to be chain reactions. You have to be careful about vanadium. You've got to be careful about MnO4 minus 1, but I told you the hack. I mean, you don't have to do that. Just always pick, never to pick the 1.67 volt equation. Just pick the 1.52 volt equation, and you'll end up with the final answer. Is that clear?
Yes.
And for most of them, they just have, I mean, they're not going to be any chain reactions. I minus 1 turns into I2, that's about it. Or I2 turns into I minus 1, that's about it. There's no further change in oxidation state. Same applies to magnesium. So for most, you don't have to do anything. But for the few examples that we did, you would have to do the chain reaction thing. But otherwise, it's going to be the same thing. Higher potential gains electrons, lower potential loses electrons. Is that clear?
Yes.
Now another, and remember, most questions are going to be kind of straightforward. They're not going to be that difficult. The things that we are doing, these are the ones that sometimes they do ask you some really difficult questions, especially the vanadium one. That was just for 3 marks. I mean, I don't think that was just for 2-3 marks, and it only appeared once in like 10 years. Now about these reactions, we've learned how to predict these reactions. So I'll just add and we'll continue this in the next class as well. So try practicing. This is your homework. Like try doing this again. I'm not going to show you the answer. Try. I mean, that's your homework. Vanadium plus Fe3 plus. So now a few and also try doing. I mean, that's a chain reaction. This one is not. Try doing chromium T2 plus with simply make it CrCl2 plus K2Cr2O7, and that's acidified. So those are your two homeworks. This one is a chain reaction, obviously. We just did that. So in the next class, we're going to study non-standard potentials. So non-standard is, remember standard conditions, that's room temperature, everything, right? Now,
Yes.
remember all of these electrode reactions, they're equilibrium reactions. And what happens to equilibriums? They get disturbed when you make a change. They either move in the forward direction or the backward direction. So the E naught at the moment is 0.77 volts. When you have a knot on top, that means standard conditions. When you remove the knot on the top, that means it's no longer standard conditions. It could be any conditions, right? So can you tell me what will happen if I increase the concentration of Fe3 plus in the solution? Where would the equilibrium shift?
Equilibrium will move forward in the forward direction. So
It's going to
Fe2
move,
plus will increase.
exactly. It's going to favor the Fe2 plus, right? Vice versa, if I decrease Fe3 plus, then the equilibrium would shift backwards, right? So the point is,
Yeah.
these equilibriums will get disturbed if you change the conditions. And if you change the conditions, the potential would change as well. Like over here, if I remove Na plus 1 from the solution, the sodium will try to make more Na plus 1, right? And to make more Na plus 1, it's going to produce a lot more electrons. So the potential over here would become more negative. Is that clear?
Yes.
So there's going to be even more electrons produced. Vice versa, if I increase Na plus 1, then the larger quantity of Na plus 1 would start attracting those electrons, right? And the amount of electrons on the electrode would decrease. Is that clear?
Yes, sir.
So we're going to discuss this tomorrow. So the point is, under standard conditions where the concentration is 1 mole per dm cube, you have a certain potential. But that potential is not fixed. That potential can change if you change the conditions. So we're going to talk about non-standard. Everything remains the same, except that the potential would either be higher or lower if you change the conditions. They're either going to be more electrons or they're going to be less electrons depending on what type of conditions you're using. Is that clear?
Yes.
So let's continue with this in the next class then. Okay, try and do those two questions, especially the chain reaction one. But just remember, don't get worried about the chain reactions. Most questions are not chain reactions. Most questions about MnO4-1, I told you the hack on that. But the other ones, they're not that important. It's important to make know how to make a reaction. Very few questions actually come on the chain reaction part. So let's continue tomorrow. Okay, take care.
Yes, sir.
Bye-bye.
Bye.